All right, we are starting chapter 10. We are going to be looking at a special case of reactions, which are redox reactions. We'll look into that a little bit more, but let's just introduce, we're going to be looking at the transfer of electrons. So we should just talk about electricity just a little bit here first. Electricity is the flow of electrons. So when you're talking about electricity, electrons are moving. You turn on the light switch, you're connecting the circuit, electrons are flowing through there. Just a couple terms that you probably have heard that maybe we should just kind of talk about really quickly. Current is talking about a rate, so some amount of charge being flowed through per second. Okay, so a unit there is the amp. Okay, that's kind of the amount of charge of 1 coulomb per second. Okay, so that's kind of thinking about the rate at which water flows, how much water would go through this hose. Okay, water is kind of a good example to use for when we're thinking about electricity flowing through a wire, but how much water can go through per second. That would be kind of like the current. Voltage, you probably heard that as well. And this is a difference, okay, so we're talking about like a potential energy between 2 points. So the difference from one to a different point would be the voltage. And so you probably also have heard of a watt, okay, so that's kind of putting the two together. So a current times voltage, or amp times volts, would be a watt, and it's kind of telling how much power output you have. So electrons flowing, this is what we're talking about with electricity. I pulled this out. This is a 2016 data. I got this, I pulled it off the internet from the Department of Energy Information. And this is just kind of showing in the US, where are we generating our electricity from? You can see that most of it, okay, you have the natural gas, the coal, a little bit of nuclear and petroleum, but most of those are all, well, as far as the coal and the natural gas and petroleum, non-renewable resources. That takes up a big chunk, okay? So we have 30 and 34% there, so 64% coming there, 20% from nuclear, just a small 15% from renewables, and I'm hoping maybe if we take this shot again in a couple years, we'll continue to see the renewable energy increase, and hopefully we'll see a decrease in coal and natural gas. So these are all ways that we can generate electricity. Looking a little bit at coal and natural gas, the next slide kind of shows a little bit of where this is going on. You can see here we have a copper wire, okay, so there's some copper wires on in a magnet, okay, and when these get turned, you can produce electrons, and then they'll flow on the wires. This is generated, but how do you get that turbine to turn to actually then produce this? This can occur at power plants. So when you're burning those non-renewable, the coal and natural gas, you burn them because they release a lot of energy, all right? And then that energy is used to heat up steam, all right? And this then can cause a turbine to turn, which then, like we see in that top one, will cause the wire to rotate, producing electrons. This also can occur in chemical reactions, and that's what we're going to be looking at in this chapter. We're going to be looking at how electrons move in chemical reactions as well. Not all reactions have that movement of electrons, but the special ones that we're talking about are called redox reactions. All right, so here we go. We are going to be looking at oxidation or electron transfer reactions, which we call oxidation reduction reactions. And for short, sometimes we will just call these redox. All right, so the RED in redox comes from the reduction here. And then the OX comes from the oxidation. Okay, so redox means oxidation reduction. And this is talking about the transfer of electrons. We are usually talking about the outermost electrons that are the ones being transferred. And you can then identify those in reactions, who's losing and who's gaining. In order for an electron transfer reaction to happen, something has to lose the electrons and something else has to gain them. You can't have just one or the other, but you can write them out in half reactions as you go. So let's just look and see here what has changed electrons. Sometimes you have to sit and identify, and we're going to go through some special rules on showing what has lost and gained electrons. But let's just look at calcium. Right here, there is no charge. Okay, and then over here it's a +2. Now, in order to go from a 0 to a +2, what had to happen? The calcium had to lose electrons. Remember, electrons have a -1 charge. So if you've now gone from no charge to a +2, you must have lost electrons. Neutral calcium has equal number of electrons and protons. Okay, look at its atomic number. In order to now form an ion, it has a loss of electrons, and since it's now +2, it has lost 2. So calcium lost 2 electrons. That means that H+ must have gained those electrons. Let's look here. It starts at a +1 charge, and then over here is no charge. So in order for the H+ to go from a +1 to a 0, it must have gained 1 electron. Now there's 2 of them, okay, so they each have gained an electron. And so that shows us that the H+ has been reduced. So here we go. Here's how you know now. Oxidation is the loss of electrons, and reduction is the gain. Now, a little way of helping students remember this, we often will say oil rig. Now, there's a couple other ways of remembering that oxidation goes with the loss, reduction goes with the gain. There's like, some tiger says grr. Now I can't remember what that one was. There's a couple other ways that maybe your high school teacher will have a different way of remembering, but the easiest one for me is oil rig. So since the calcium has lost electrons, it was oxidized. And since the H+ has gained an electron, the H+ is reduced. All right, we're going to look at a couple more examples. We're going to do one with a demo next, and then in the next couple of videos, I'm going to show you ways to identify oxidation states to see what is gaining or losing electrons. All right, we are going to do a little bit of a demo here to illustrate our redox reaction that we have going on. So I want to just kind of set this demo up because it does take some time for the reaction to start to go. So this reaction is going to have silver nitrate and copper wire. So this is solid copper. You can see it's shiny, it's copper color, it's bendable. I made it into some type of shape here that you can see. And we also then have a solution of silver nitrate. So I'm going to pour the silver nitrate into the beaker. So here we just have a plain beaker. Our silver nitrate here. Look at the solution. If you can see, it looks very clear, and it is, but it has silver nitrate dissolved in water. So we have an aqueous solution of silver ions and nitrate ions. I'm going to just set that down. We're going to stick our copper wire in here. See if I can get it to stay in there like that. Yeah, it's going to hang out like that. All right. So far, you don't see anything really changing too much. It does take some time, so we're going to come back to this. But we're going to watch and see what happens. So I'm going to put this off to the side, and let's look at this reaction in a little bit more detail. Voila. Okay. Top on here. Silver nitrate plus copper. If you have a guess on what type of reaction this is, you have an ionic compound, silver nitrate, and copper is by itself. So if you were going to guess, you would probably be saying that, hey, this is a single displacement reaction. Copper is going to come in, displace the silver. All right, so let's write the products out. If it's going to displace the silver, that means silver is going to be by itself. So this would be solid silver. And what's left over? Now the copper and the nitrate are going to go together. The copper here is going to form a +2. So we're going to need Cu, and then we're going to need 2 nitrates since they're each -1. All right, so since we have 2 nitrates, it looks like we need to put a 2 right here, and then a 2 here to get this to balance correctly. All right, if you look at this reaction, can you see, hey, this is a redox reaction? Maybe not yet, okay? But what's going on as far as redox, which we have said is a transfer of electrons, what's going on? So sometimes it might help to write the net ionic equation here. So let's go and write our net ionic. All right, our net ionic is when we leave off the spectator ions. The spectator ion is a thing that is not changed at all in the reaction, so it would be aqueous on both sides. And if you look, silver is aqueous over here, but now it's a solid, not a spectator. Same thing with the copper. It's a solid over on the reactant side, and it's aqueous on the product, so it changes. The only thing that stays aqueous on both sides is the nitrate. So we'll leave that off. What do we end up with? We have silver nitrate here, so the silver is a +1. Is reacting now with the copper, which is solid, and on the other side now we have 2 Ag and copper ions. So this redox reaction is taking place, and now when you write the net ionic, you can kind of see a little bit where the electrons are going from. Initially, silver has a +1 charge. So initially, we have Ag, and it starts at a +1, and then on the other side of the reaction, it's a solid with no charge. All right, if it's gone from a +1 to a 0 charge, what has happened as far as the electrons go? Has it gained electrons or has it lost electrons? Okay, so you have to remember electrons are a -1 charge. So if it has gone from a +1 to a 0, it gained electrons. Now there was 2 silvers, okay? So each silver gained 1 electron. All right, so that was a total of 2 electrons that were gained. Where are these electrons coming from? Well, let's check out our copper. Initially, this was a solid with no charge, and it went from no charge to over here a +2. So if it goes from a 0 to a +2, it must have lost 2 negative charged electrons. To now be a +2 charge. All right, so each of the silvers, there was 2 of them here, gained an electron. Okay, so that was 2 electrons gained, and those electrons came from the copper. It started off as a 0, went to a +2, lost electrons. So as far as redox goes, oxidation reduction, let's go back to our oil rig. Okay, remember this? All right, oxidation is the loss of electrons, which means that the Cu was oxidized. And the gain of electrons, reduction is the gain of electrons. Each of the silver +1 gained an electron, so Ag plus was reduced. All right, so here's our balance equation right here. We're going to at some point be writing half reactions, and I'll show you that later on. We can look at this reaction now, see where the electrons are moving from. What gains the electrons is being reduced. What loses electrons is being oxidized. What do we expect as far as this reaction goes? So see if I can hold this up. It's starting a little bit. I'll kind of find a spot right here. I'm not sure if you can see it too well. That copper wire that's now in the solution is starting to have something form on it. And we'll look back and it'll be a lot better to see. But some crystals are starting to form. Well, that is our silver crystal starting to form. And you can't really tell quite yet, but we're going to be able to see something else. In solution, we're now forming copper ions. And if you know anything about the copper ions, they're going to be a blue color. So as this reaction takes place, we're going to start to form solid silver, and we're going to be starting to see copper ions go into solution. All right, so there's the end of that example. We'll continue on with more redox. Just to come back to that silver, nitrate, and copper wire demo really quick. it has started taking place, and we can now see the reaction has started happening. You can see the silver crystals that are forming on the copper wire. And we can also tell that the copper has gone from a solid copper into solution, because now you can see it was a clear solution, and now you can see it being a light blue solution due to the copper ions there. So we did this redox reaction. We're going to come back and look at it one more time in a couple more videos.